Hi dear students, in this class I am going to explain about rectifiers. Among rectifiers, first one is half-wave rectifier. So I am going to explain half-wave rectifier. I am Dr. B. Ravi Kumar, Associate Professor, Department of SC. Coming to rectifier, if we are going to start rectifiers, what is the need for a DC source? When we think about it, the DC source is required for all electronic devices. Yes, it's true. For the operation of the most of the electronic devices and circuits, a DC source is required. All of the electronic devices are operated with DC sources. So it's advantageous to convert domestic AC supply, which is available from our switchboards like power transmission lines and connected to the main supply, which is converted into DC voltages or DC sources. How to get DC source? The process of converting alternating current or AC voltage or AC current into DC voltage is called as rectification. When we are performing this rectification using the electronic circuits, we will achieve the DC source. A circuit which converts AC voltage of main supply into pulsating DC voltage using one or more PN junction diodes is called rectifier. Now we will see that how this rectifier which converts AC into pulsating DC and then which will be further processed with some other circuits to achieve DC power supply, which will be useful for our electronic devices. When we see this, any mobile phone or any laptop, all are operated with a DC supply which is connected through adapters or charger. The charger input is AC supply from the switchboard and output of this charger is DC supply, which is required for mobile phone. Similarly, adapter takes the AC input signal from the board and which gives the required power to laptops. Likewise, so this entire adapter which converts AC into perfect DC. Among those blocks, one of the heart of the circuit, which is nothing but rectifiers. Now we will see that and study what is rectifier and how many types of rectifiers. So what is rectifier? Rectifier is an electronic circuit which converts an AC signal into pulsating DC signal, an AC voltage into pulsating DC voltage. Basically, there are three different types of rectifiers: half-wave rectifier, full-wave rectifier, and a full-wave bridge or simply bridge rectifier. Based on the number of diodes which are used in this rectifier and based on the number of cycles which rectification of a given AC input signal, which can be classified among these categories. First, we will see that half-wave rectifier. So, before going to perform the operation of the half-wave rectifier, just we study about what is AC supply and how it represents of this AC supply. A signal obtained from main AC supply is purely sinusoidal that can be defined in terms of peak amplitude and frequency. Peak amplitude measured along the y-axis and frequency along x-axis. Now what is peak amplitude? The maximum amplitude of an alternating signal on either sides measured from its zero value or origin value. So this in positive direction, in a negative direction. So the maximum value of this amplitude of an alternating signal can be represented by peak amplitude. And the frequency, number of cycles that passes a given point per second or number of cycles per second from origin in per second. It is mathematically expressed as of signal, any voltage signal V of t is equal to A sine omega t, where A is an amplitude and omega t is a frequency in radians. So as shown in the figure, it is a pure sinusoidal signal represented with the positive cycle and negative cycles. And the time period of this AC signal, AC supply is fundamental time period for AC signal is T by 2. Oh, sorry, T, capital T. So one full cycle, one positive cycle and one complete negative cycle, which is represented by a fundamental time period capital T. For in a general case, so AC supply always almost around 220 to 230 volts and 50 hertz in India. So when we take 50 hertz frequency, then in fundamental time period T is equal to 20 milliseconds. So when we take the supply, we measure this peak amplitude A is equal to 230 into root 2. This 230 volts a rated voltage coming from the supply. When we multiply into root 2, we'll get the peak amplitude or maximum amplitude of the signal, which will be given to the diode or rectifiers. With W is equal to 2 pi f radians per second. This kind of AC power supply signals are given to rectifier circuits. Ideally, this mathematical representation of AC signal by sinusoidal or cosinusoidal, but practically, so it's not exactly represented of this AC signal with the sinusoidal and cosinusoidal signals. For the purpose of analysis, we can take that as this time varying signals can be represented by A sine omega t. And also, two important parameters for these signals for time period for this instantaneous of the signals, so which are called average or DC value of this particular power supply signal or any signal, the root mean square of this kind of sinusoidal signal. The average or DC value, the DC value of a signal V of t is the average value of that signal. If you consider a discrete points like 1, 2, 3, what will be the average? Average is equal to sum of these points by number of count. Similarly, here also it is a continuous instantaneous values of the signals, infinite number of instantaneous values of the signals. So we can measure instead of summing of these points, so we can use integration. So integral of all points, infinite number of points over a particular time period, fundamental time period, which is represented by 0 to capital T. And the signal represented in this case is sinusoidal signal, so which is represented as V of t into dt divided by total number of counted discrete point. Similarly, we can take total time period capital T. This is exactly what this V average or VDC, which is equal to integral 0 to time period capital T for the signal V of t dt divided by 1 by time period So which is represented as average, or simply we can call it as VDC. So, and also we can suppose the time period is in radians, the time period which is capital T is equal to 2 pi. Then this average V average is equal to VDC is equal to 1 by 2 pi integral 0 to 2 pi. V of t d omega of t. And the root mean square values of the signal Vft mathematically evaluated as Vrms is equal to square, where name itself says that root mean square. First we will see that root, this is the root, and mean nothing but integral of signal dt by divided by 2 pi is represents the mean, and square of the signal v of v square of t dt. So all these parameters include in this value. So this root mean square of the signal will help us to find out some parameters in the rectifier output. So V average and Vrms are the important parameters for the any signal, then which will be useful for the analysis of that rectifier. Block diagram of DC power supply. When we see this block diagram, it is simply represented of a simple charger or adapter can be put into one place, then this diagram which represents this similar. What is DC power supply? The elements which are in this DC power supplies are transformer, rectifier, and filter, and regulator, and which is connected to load. The four important elements which are used in DC power supply, and among those elements, a rectifier is the heart of the element in the DC power supply, which converts AC signal into pulsating DC or DC power supply. So this step down transformer and rectifier and filter regulators. First we will simply see that what is rectifier, what is a transformer. Transformer which converts AC signal into AC signal. There are two types of transformers, step down and step up transformers. Step up transformer which transform a lower AC signal into higher AC signal, and step down transformer will higher AC signal into lower AC signal, so which converts AC to AC. So generally power supply is available with the parameters 230 volts and 50 hertz frequency. This large power supply 230 volts is not required for conversion of this DC. We need to step down the 230 volts to 20 volts, 10 volts, 9 volts, 5 volts based on the requirements. So in order to do that, we have step down transformer which converts 230 volts to that step down to 20 volts or 10 volts. And then the output of this lower value of AC signal is given to rectifier, so which converts, which rectification in this element. Then output of the rectifier having AC component and DC components, so which is not required for which is not required for electronic input. So we need to reduce those AC components which are available in the rectified output. So that's why we go for filters, which may be different kinds of filters, and then which is the output of the filter again still remains a small ripples. The output with the small ripples given to regulator, just like a Gino regulator. That's why we have shown Gino symbol, Gino diode symbol. Then output of the regulator, which will give a perfect DC, we can represent with this perfect DC. This perfect DC given to load resistor. The load resistor may be anything, which may be like LEDs, which may be mobile phone, which may be laptops. So whatever the electronic loads. In this case, so all the elements which are used in this power supply block. Coming to half-wave rectifier. So in order to perform the signal which is coming from AC power supply to DC power supply, immediate after this step down transformer, the next block is rectifier. So now we will see that how this rectifier circuit which converts AC to pulsating DC. Half-wave rectifier. First, half-wave rectifier connection. What are the circuit diagram for half-wave rectifier, which includes a transformer and one single diode and load resistor connected in series. And AC power supply is given to primary coil of this transformer, and peak voltage will measured in secondary coil that will be given to diode and then connected to load resistor. So half-wave rectifier requires only one diode and which is connected to load resistor. The process of removing one half of the input signal to establish a DC level is called half-wave rectification. Now see that how this diagram which converts AC signal into that pulsating half-wave rectification. Operation during positive half cycle of the AC input signal. During positive half cycle of the AC input signal, diode is forward bias because this during positive half cycle, which represents the positive instantaneous voltage or current, is given to diode, when plus is given to diode P type, the plus is given to P type, the diode is set to be forward bias. When diode is in forward bias, so according to the operation of the diode, which allows the flow of current from P to N, then the direction of the current flow in the P junction diode is this one. When it allows the current flow in during positive half cycle, so that the current flows in the load and produce voltage across load. Whatever the current passing through the diode and the same current passing through the load resistor. So I into the diode current and into RL, which is represented with the voltage, V out voltage. Whatever the instantaneous current passing through the P junction diode, the same kind of positive current flow in the load resistor, and current into resistor will get same instantaneous cycle of output voltage. Similarly, during negative half cycle, of the AC input signal, the diode is reverse bias and conducts for which does not conduct all instantaneous voltage. So in the reverse bias, what happened during negative half cycle, the diode is in negative is connected to the P terminal. When diode is connected with the P terminal, it is said to be reverse bias. When diode is in reverse bias, it will act as a open circuit. So when we act as an open circuit, no direct connection, so no current flow, zero current flow in the loop. The zero current into load resistor, the 0 volts. So the voltage is, output voltage is equal to 0 volts. When 0 volts, and during negative half cycle, it shows that 0 volts in the output, rectified output. This process is a repeat for, again, positive half cycle, you will get the same positive output in the load resistor, and during negative half cycle, it will be 0. So, in the half-wave rectification, the rectifier conducts current during positive half cycle of the input AC signal only, and negative half cycle is suppressed. So which allows only positive half cycle, and it suppresses the negative half cycle. That's why the name called half-wave rectifier, which rectifies only one half cycle. Remaining half cycle gets suppressed. Coming to the analysis of half-wave rectifier. So far we have seen that this type of AC input signal given to the rectifier, this type of pulsating DC output available across the load. Now, by seeing this waveform, we can't justify that how much best the circuit is and how much the best the output is. How can we justify, how can we say that this half-wave rectifier is best for rectification? So from mathematical analysis, we can clarify that, we can say that, we can determine that the rectifier is best suited for rectification or not. Now we will see that. Consider an AC sinusoidal input signal V of t mathematically is equal to Vm sin omega t. If you take this kind of sinusoidal signal mathematically, considering Vm sin omega t, and the rectified output as shown in the figure this way. Now find the DC voltage and find the RMS voltage and ripple factor and efficiency, peak inverse voltage for the rectified output. Based on those parameters, we can conclude and we can say that this rectifier is useful for a practical application. Now find out each one by one and then conclude that this rectifier is good or not. First we will find out V average of the rectified output and how much DC component and how much DC voltage generated at the output, and what is the RMS value generated at the output, and find out the ripple factor and then efficiency and peak inverse voltage. What is V average? As I said previous, fundamental formula for V average is nothing but integral of 0 to time period capital T or 2 pi in radians for the given signal Vm sin omega t d omega t divided by total time period 2 pi or capital T. So this same formula we can apply here. V average or VDC for this particular rectified output. What will be the time period for rectified output in radians? When we see this start from origin, first cycle represented with pi and remaining suppressed cycle 0 signal, then the time period is 2 pi, then 3 pi. Likewise, when we see this, what will be the time period for this rectified output is one completes half cycle and 0 cycle. This can be repeated again. This can be repeat again. Sorry. So the same signal repeat once again. So that's why this kind of shape is repeated. That's why the fundamental time period is kept 1 by 2 pi. So V average is equal to 1 by 2 pi integral 0 to 2 pi Vm sin omega t d omega t. Take the Vm constant term to the left side, Vm 2 pi, and integral 0 to 2 pi sin omega t d omega t. When we see the rectified signal, the signal is available, peak signal is available during 0 to pi. What about this during pi to 2 pi? During pi to 2 pi, the value is 0. So we can integrate only 0 to pi. Then find out this integration. Apply the integral 0 to pi sin omega t. What is the integration for sin omega t? Sin omega t minus cos omega t. Apply the limits. Integral 0 to 2 pi. When we apply the limits, it's pi. Minus of cos pi minus cos 0 So then cos pi minus 1 cos 0 1 minus 1. So it is minus 1 minus of 1 minus 1 minus 1 minus 2 multiplied by minus. You will get this value will get Vm by 2 pi into the resultant value is 2. 2 to cancel, you will get Vm by pi. Vdc is equal to Vm by pi for half wave rectified output. And we measured in currents, DC current flow in the load resistor IDC is equal to Im by pi. When we take the IDC, VDC by RL and VDC by RL, we can represent it with Im. So IDC is equal to Im by pi. These are the important parameter for DC component in the rectifier output Vm by pi. In deriving the average values of the output voltage and load current, we have assumed that the diode used in the rectified circuit is an ideal one. So when we used ideal one and when we assume that it is an ideal one, it has zero forward resistance and infinite reverse resistance. However, in practical applications, in practice, it's not so. If RF is the diode forward resistance and it should be considered, then the average output voltage across the load is taken as VDC is equal to Vm by pi minus IDC into RF, whatever the current flow, DC current flow in the diode resistance. So when we see this figure, for example, it is a practical diode. It has RF, forward resistance, and RL. If you see some power supply here, AC power supply, and connected in series with two resistors, what will be the total voltage by applying KVL? So power supply voltage is equal to drop in the forward resistance I into, for example, we focus on DC current, DC into RF minus I into plus IDC into RL. So this kind of drop. So this drop is, so total voltage drop across the forward resistance and drop across the load resistors. So when we want to find out what will be the DC output voltage, so we must answer total, we can subtract the total voltage to the drop voltage across diode. So whatever the DC voltage obtained across the load without forward resistance will get Vm by pi. So definitely when we find out, when we consider the forward resistance of the diode, so we can automatically subtract those drop available in the forward resistance of the diode. So that's why I am considering Vm by pi minus IDC into RF. This much of drop can be neglected. This much of drop can be subtracted from the DC voltage available across the load without considering of practical diode resistance. So when we subtract this one, it will be consider that RF of the diode resistance in the network. Then what is the IDC? IDC is nothing but Vm by pi in earlier case. Now it is Vm by pi into RF plus RL. RF is the forward resistance and RL is the load resistance. So when we take this one, consider this forward resistance and load resistors, and then you will get the DC current output. If the AC input voltage is applied through transformer, then it is necessary to include the secondary winding resistance. So when we consider secondary winding resistance also, then the network will look like secondary coil resistance, diode resistance, and load resistor, and supply. For example, this is the supply. This is the supply. So this loop, which includes total 3 resistors, are in series. Then in this case, this DC voltage VDC is equal to Vm by pi IDC into RF plus RL, and then when we find out the average value of the load current, which is represented by Vm by pi into forward resistance, load resistance, and secondary coil resistance. Simply we can include all those parameters. So when we neglecting this one and when we neglecting this one, IDC is equal to Vm by pi into RL. Vm by RL is nothing but Im. So Im by pi. We achieve Im by pi. Next parameter we need to calculate for those rectified output, the average value of the voltage measured across the load resistor. Similarly, what will be the RMS value of the across the load resistor. Vrms is equal to square root of 1 by 2 pi of an interval of this rectified output, integral 0 to 2 pi, square of the signal, Vm square sin square omega t d omega t. What will be the sin square omega t is nothing but 1 by cos 2 omega t by 2, and this constant and take the left side. So Vm square by 2 pi. And then when we integrate of these two terms, it has two terms, 1 minus cos 2 omega t by 2. So this among these two terms, when we integrate those two terms, first term is integral of 1 by 2. 1 by 2 is the constant, so we will take omega t and apply the limits 0 to 2 pi. And here it is a half-wave rectifier. We can consider that the signal available only for pi. So then the limit is 0 to pi minus what will be the integration of cos 2 omega t. So it will be the sin 2 omega t. So when we apply the sine signal, sin 2 omega t by 4 and apply the limits 0 and pi. In this case, the upper limit of sin 0, sin pi 0, and lower limit of 0 of sin 0 0. So entire thing will become 0. So when entire things will become 0, then what will be the first term 1 by 2, integration of 1 by 2 omega t, limits 0 to pi, pi minus 0, you will get pi. When we take this pi and multiply with the square root of Vm square by 2 pi into pi, then pi cancel. Already it will be the pi, already constant is there, pi by 2. Here we got pi by 2. So pi cancel. So Vm square by 2 square, which is nothing but Vm by 2. So Vrms is equal to Vm by 2. So this is equal to square root of Vm square by 2 square, which is nothing but Vm by 2. So what will be the VDC is equal to Vm by pi and Vrms is equal to Vm by 2. Now these two parameters can be applied or can be substituted in the ripple factor. This is the most important parameter to analyze the rectifiers. What is ripple factor? Ripple factor is a factor which measures the amount of AC component or AC content present at the output of the rectifier as compared to the DC content or DC component present in the pulsating in the rectified output. So simply we can say that what is the ratio of VR RMS by VDC, and the ripple factor is the ratio of how much AC component in the rectified output divided by DC component in the rectified output. Always AC component measure in RMS, that's why I am taking in the numerator VR RMS. VR RMS nothing but V ripple RMS. So always AC value measured in RMS, and R nothing but ripple nothing but AC component. That AC component VR RMS, a ripple of that RMS divided by VDC. So how much AC component in the rectified output divided by DC component is nothing but ripple factor. And this VR RMS mathematically represented as square root of VRMS square minus VDC square divided by VDC, and take this denominator term into the numerator term. So we'll achieve that this ripple factor gamma is equal to square root of VR RMS by VDC whole square minus 1. This is the most important formula useful for problem solving. How much ripple factor for a given data. Square root of VRMS square by VDC whole square. Square root of VRMS square by VDC square minus 1. Or square root of VRMS by VDC whole square minus 1. So what we have already rectified as half-wave rectified output, what will be the VRMS, which is equal to Vm by 2. So we got Vm by 2. Substitute Vm by 2 in VRMS and Vm by pi in VDC, and solve this square root equation, then you will get square root of pi square by 4 minus 1, which is equivalent to 1 pi 21. When we represented in percentage, it is equal to 121% of AC component, or 1.21 AC component value will be there in the rectified output. So ripple factor will get 1.21. So when we now we can conclude that gamma is equal to 1.21, which represents that large AC component as more than our expected. So more than expected of AC component available in the rectified output. That's why not at all useful this half-wave rectifier for practical applications. This kind of rectification, this kind of ripple factor will never be used for rectification. But it is a basic circuit. So based on which we can upgrade, we can enhance the circuit, we can improve that circuit to full wave rectifier and a bridge rectifier. And another important parameter is efficiency. Efficiency, it is the ratio of DC power delivered to the load to the AC input power. So as the formula says that how much DC power delivered to the load by providing this rectification and of a given AC input power to the rectifier circuit. The efficiency signifies that the outcome of the rectifier circuit to output DC power in compared to AC input power. So the efficiency formula PDC by PAC. PDC nothing but this is not there. PDC nothing but VDC square by RL. VDC square by RL divided by VRMS square by RL. So P is equal to V square by RL, I square RL. Likewise, I am taking VDC square by RL divided by VRMS square by RL. And so here RL and RL cancel. Then VDC square by VRMS square. We have VDC Vm by 2. VDC Vm by pi, and VRMS is Vm by 2. So when we Vm cancel, so we have 1 by pi square by divided by 1 by 4. So when we take the interchange, then 4 by pi square. This 4 by pi square which is equal to 0.406. So efficiency PDC by PAC into 100 in percentage, you will get 40%. So among 100, you will get only 40% of DC is obtained in the rectified output. So again, from this parameter, from the efficiency, we got only 40% of DC component available in the rectified output. So we can't use in practical applications. Peak inverse voltage. This is the how much reverse voltage sustained of those diode. When PN junction diode is in during positive half cycle, it acts as a forward bias. During negative half cycle, the diode acts as reverse bias. So this peak voltage is applied to reverse voltage of the diode. At what extent it will be sustained in the during negative half cycle or reverse bias. So when we goes on increasing the negative half cycle, so large negative voltage is given to diode, so it will goes to breakdown voltage and then diode gets damaged. So what is the maximum extent of the reverse voltage can be represented by peak inverse voltage, so which is equal to Vm. So that value of the Vm is given the specification sheet. So these are the important conclusions from those half-wave rectifier analysis. The ripple factor of the half-wave rectifier is 1.21, which is quite high. And the output contains a lot of ripples. The maximum theoretical efficiency is 40% only. The practical value will be quite less than this also. So this which indicates that the half-wave rectifier is quite inefficient for practical rectification process. So that's it. This about half-wave rectifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.